Swayam Prabha. Digital India. Educated India.
So welcome back everyone, and in this module let us continue our discussion related to the examples. We'll right away jump into the examples, some illustrative examples highlighting the application of the theory we have just developed, that is on angular momentum. So the first example is that of we are given a hollow sphere. So a hollow sphere of inner radius A and outer radius B is made of material of uniform density rho. The sphere is spinning with angular velocity capital omega, and it is about an axis which is passing through its center. See, whenever we talk about and finding angular moments and so on, we definitely need to prescribe the axis of rotation. So about an axis fixed through its center Okay, so we need to find the angular momentum about this axis. Okay, so so what we have is we essentially we are given a hollow sphere. So it's not exactly a sphere, but it's a 3D annulus. So we can essentially find the formula for the solid sphere and subtract the component of the the space, which is the this shaded region. Okay, so we have the inner radius being A and the outer radius being B, and we see that the moment of inertia of the solid sphere is 2 by 5 m sphere r square, r being, so this is the moment of inertia of the solid sphere, right? So now we can find that from here the moment of inertia of the hollow sphere. As I just said, we just find the moment of inertia of the outer sphere and subtract the hollow part from the sphere. So this is going to be, the hollow sphere will be 2 by 5. So I is 2 by 5 capital M B square minus 2 by 5 M A square. Okay, so so what we have is, our capital M is the mass of this sphere, the solid sphere. So our capital M is, we can relate this capital M and small m with the density as follows. So we have 4, so we are talking about sphere, so this is 4 pi b cube by 3 times rho, and small m will be 4 pi a cube by 3 times rho being the uniform density which is cut out from the sphere. So then we can plug all these quantities here, and we are going to get the moment of inertia will be 8 by plugging everything. So this will be 8 by 15 pi times rho times b5 minus a5, and this is a standard problem where the axis of rotation is fixed about its center, and it is given that the angular velocity is omega, so we have the angular momentum will be nothing but I times capital omega, and that is what we had to find. It's all about finding the moment of inertia in this problem. Okay, so then let us look at another issue here. The issue related to the moments of the rate of change of angular momentum. So from the angular momentum principle, what we see is d L naught dt is d dt summation Ri cross Mi Vi, right? So what we see is I from 1 to n, and then we can similarly write. So now we are trying to find the time derivative of the angular momentum, right? So what we see is that this is going to be summation I from 1 to n Ri cross Mi dvi. Well, we'll have to take the chain rule here, or sorry, the product rule. We are distributing the derivative here. So the first component and then the second component will be summation Ri dot cross with Mi Vi. But notice Ri dot is nothing but Vi, so Vi cross with Vi will be 0. So this second component will be 0, and all we are left with is the first component. So we see that from second law, Newton's second law, we find that Mi Vi dvi dt is nothing but the external force acting on the particle I, and this is the external force acting on the particle, external force, and we could also have some internal force contributions, which is summation j from 1 to n gij, right? And we see that dl naught dt, this angular momentum is summation I from 1 to n Ri cross with, we have now plugged everything. We are plugging this formula, which is what we are substituting here, into this, and we see that this is Fi plus summation Gij, right? And again, let us distribute the cross product here. So we get that this is Ri cross with Fi plus summation I from 1 to n j from 1 to I minus 1 Ri minus Rj cross with Gij, right? So what we have done here is we are trying to find the internal contribution here, right? So Gij was summation over j from 1 to n. So that is what we have. Now what is happening is the internal forces Gij, they are parallel to the displacement. Their direction, Gij's direction is parallel to the displacement, parallel to Ri minus Rj. So it's parallel to the displacement, and we see that this we expect, since because of this condition, we expect that the second quantity will be 0. The cross product of two parallel quantities will be 0, and all we are left with is this quantity. Let us call this as k0, the moment due to the external forces. So what we get from this exercise is dl naught dt is the total moment due to the external forces, Fi. So let us write this. This entire exercise can be written in a single statement, which is the angular momentum principle. So what it says, angular momentum principle, is that in any motion of s, the rate of increase the rate of increase of s is increase of s about a fixed point. The rate of increase of s about a fixed point equals the total moment due to the external force acting on s. Due to the external force acting on s. So dl naught dt is equal to k0, external force acting on s. Okay, so similarly, as we just saw that for at any other point, we see that at any other point a, we see that ka is k0 minus a cross f, and we see that la, the angular momentum at that second point is going to be L0 minus A cross P. Okay, so what we get is, from here we can see that Ka, let us do this exercise. So Ka minus La dot, let us see what this value is. So Ka minus La dot, so we can plug in the value of La and Ka will be equal to K0. So Ka is K0 minus La dot is L0 dot plus, well, not plus, but minus A cross F minus P dot, right? So what we saw was K0 was equal to L0 about the origin and F, the external force F is equal to the rate of change of linear momentum. So that is from Newton's second law, right? We see that F is equal to P dot, and so this is also 0, and we see that this is 0. So what we see is that the angular momentum principle Ka is La dot. It holds for any point, not just the reference point or the origin, but any point, any other point as well. So that is the beauty of this relation, that we can shift, we can translate and still apply this principle at a new point. The formula remains the same. Okay, so in particular we can talk about the angular momentum about the center of mass. So what exactly is that we are talking? So angular momentum about the center of mass, right? So the problem says we can write this statement in the form of a theorem. It says that suppose a general system of particles, of S has a total mass m, and its center of mass G has position vector r and velocity v, right? And then the angular momentum of S, about the origin O, is or can be written in the form LO is R cross MV plus LG. So what are these points? I think it's fairly clear. R is the distance of the center of mass from the origin, and V, of course, is the translational velocity of the system of particles from the translational velocity of the center of mass. And LG is the angular momentum. So it's the angular momentum of S about G in its in its motion relative to center of mass, relative to center of mass. Okay, so Lg is the motion relative to center of mass, and so the first part of this formula is the motion of the angular momentum of the center of mass of the system, and the second is the contribution from the internal distribution of the particle, that is the angular momentum due to the internal distribution with respect to the center of mass, or the motion relative to the center of mass. So we saw that in particular, we saw that when the only force acting on the particle, sorry, when so when we have the only the only component of the force acting on the particle is the weight of the system, just the weight of the particle, then the motion, we will only get the moments due to the first component here, that is due to the center of mass, and the moments due to the second component will vanish. We'll just revisit that example shortly. So what I just said is, so let us look at the quick proof of this theorem before proceeding. So the proof is as follows. Suppose since Lg is the angular momentum relative to the center of mass, so Lg is summation mi ri minus r cross with vi minus v, right? And what we see is, so Lg is the motion relative to the center of mass. So we have already subtracted the position vector of the center of mass, and we have subtracted the velocity component as well. Okay, so then of course we need to take the cross product. We simplify this expression. We see that this is L naught minus mr cross v minus r cross mr cross v. So let's put all the brackets. So r cross mv plus m times r cross v. Okay, so what we get is two of these quantities will cancel out, and we are going to get that this is going to be L naught minus I think will eventually be left with r cross mv here, and I think that is the end of this proof here. And we can quickly term these quantities. So we can see that this quantity r cross mv is the translational component of the rigid body, translational component, and lg is the rotational, this is the rotational component of the rigid body. Okay, so what we see is, as we saw, that when we talk about the translational component of the angular momentum, it is as if we are just talking about the translation of the center of mass of the system, and the rotational component is the contribution of each of the particles about the center of mass, right? And then so what we have is that mv dot is for the rigid body, this is these are the angular momentum. So for the force balance, we find that the translational component is given by m times v dot is F, Newton's second law acting on the center of mass, and the rotational component is going to be Lg dot is going to be kg, right? So these are the translational and the rotational component relative to the center of mass. So this is relative to the center of mass. Okay, so let us revisit our problem where the only force acting on the system is the weight of the particles. So the problem again says that we have a rigid body is moving in any manner. A rigid body is moving in any manner. The exact motion is not given, but it is moving under uniform gravity. It is moving under uniform gravity. Show that its motion relative to its center of mass is the same as if gravity were absent. Okay, so then we see that so what we have is so we need to describe the motion of such a object which is only experiencing gravity. So again, if we go back to our previous example, what is our previous example? The example where we few slides back. So this is, let me call the previous example that we are referring to is which one is that example? We have few slides back. So we are talking about here. So we are talking about this particular example few slides back. Let me call this example number star here, right? So coming back, so from our example number star from one of our just previous module, we see that under uniform gravity, the total moment of gravity forces about any point on the body were the same as if they all are acting at G, the center of mass. So this is our center of mass. So what we saw was our kg, the moment about the center of mass is going to be r cross minus mgk. So that is what we saw from this example star that we have just tagged here. And we see that of course we can keep this center of mass, we can choose our origin such that this position vector of the center of mass G is 0, right? So it's a 0 vector. That is how we chose. So that is our origin. And in that case, if that is the case, then the rigid body equation, the force balance could be written as m times v dot m dv dt is the net force, which is minus mgk. The only force, remember, the only force acting is the weight of the particles, and the force relative to the center of mass is going to be the rotational component. We call this now, I add a new term. This is the rotational component of the force balance, or we call this as the torque balance. So I add the word torque balance. One and the same thing. This is the same as the relative component of the center of mass. So that is the torque balance. So the torque balance gives us that dlg dt is 0. So dlg dt is 0, right? So that is what we have. So dlg dt is 0. Why? Because our kg is 0. The net torque is 0. Okay, so and with this setup, it's quite clear now. The motion is acting. The motion of the body is such that that the entire force is being acting upon its center of mass only. So the motion of the body, the rigid body, is such that it is a point object with the entire point object point mass concentrated at the center of mass. Okay, so let me call this as star. Okay, so let us we have few minutes remaining. So what we can do is, well, we have a new topic at discussion, but something we'll put it in the next module. Just to give you an idea what's coming in the next module, we will be talking about some application of these angular momentum principle, and also the moment of force or torque example. So thank you so far for listening.